Assalamualaikum YouTube viewers. Today in this video I am going to describe the steady state Schrodinger wave equation. So in this video we are going to derive the steady state Schrodinger wave equation. Okay, so first of all what you need to know is that psi, okay, as we have read in the earlier video that if psi has a bar above and below it, it means that the psi is dependent upon the position coordinates as well as the time coordinates. Okay, if I have a simple psi like this, it means that this psi only depends upon the position coordinates, and if I have a psi with a bar above and below it, it means that my psi depends on the position coordinate as well as the time coordinates of a system. Okay, so this psi depends upon time. It means that it evolves with time, it changes with time. Okay, so the next thing is, for every system, time dependent Schrodinger wave equation. This is the general form of time dependent Schrodinger wave equation, in which Hamiltonian operator operates on psi when gives out minus h cut over iota curly psi over curly t. Okay, so now our Hamiltonian operator depends upon is a function of position coordinates, okay, and the time. Okay, since we are talking about psi that depends on position coordinates and time, so I can say that my Hamiltonian operator is a function of position coordinate and time. Okay, so as you know that Hamiltonian operator, what is the value of Hamiltonian operator? Hamiltonian operator depends upon is equal to kinetic energy plus potential energy. Okay, the Hamiltonian operator is equal to kinetic energy plus potential energy. So what we are going to do is just to plug in the value of Hamiltonian operator, the final value of Hamiltonian operator. Okay, what we have to do is to write the value of kinetic energy operator and the potential energy operator and put it the value of Hamiltonian operator as a whole here. Okay, so when putting the value of Hamiltonian operator here, you get an answer equal to minus h square over 2m del squared plus v, and v here represents the potential energy and this part here represents the kinetic energy. Okay, this part here represents the kinetic energy, as you have read in the previous videos on time independent Schrodinger wave equation. Okay, so and this part v depends upon the position coordinate x, y, z and also the time. Okay, so this is the value of Hamiltonian operator that is being applied on psi. Okay, so this Hamiltonian operator is being applied on psi, and this one is equal to minus h cut over iota. Okay, this is minus h cut over iota, and curly here is my derivative, and psi as you know that it depends upon x, y, z and time, and divided by curly t. Okay, so as you can see that this equation is a partial differential equation. Okay, as you can see that this equation is a partial differential equation that contains both position as well as the time variables. Okay, as you can see that it contains position, x, y, z position variables and time variables, and on the right hand side it also contains position variables and time variables. Okay, so what we can do now is in order to solve this equation, okay, what we need to do is to separate it into two differential equation. Okay, we need to separate this whole equation into two differential equation, in which one equation will contain only position variables and the other equation will contain only the time variable. So how can we do this? First of all, as you can see that here on the left hand side we have potential energy with x, y, z and time coordinates, and on the right hand side we have here psi with x, y, z and time coordinates. So what we need to do is just to cancel out the position variables on the right hand side of the equation. We need to cancel out the psi x, y, z on the right hand side of the equation, and we need to cancel out the time coordinates t on the left hand side of the equation. In this way we will get two equation in which one will contain only position coordinate and another will contain only the time coordinate. Okay, I am repeating this, that what we need to do is just to cancel out the position coordinate on the right hand side of the equation, and we have to cancel out the time coordinates on the left hand side of the equation. First of all you need to do is to break up this psi. Okay, how can we break up the psi? As you know that psi here depends upon the position coordinate x, y, z and also the time coordinate. So by breaking it we can write it as that this part here is equal to psi x, y, z Okay, so this part here is equal to psi xyz multiplied by phi into time. So we can break this into two functions. One is psi dependent upon position coordinates, and the other function is phi that depends upon the time coordinates. What we have done is just to break this value up. Okay, we have just broke up this function into two functions. Okay, so the next thing that we are going to do is just to plug in this psi's value, this value here in the first part. Okay, this is my equation number 1. So what we need to do is just to put this value of equation number 2 in equation number 1. Okay, this value will be put here. So after putting the value, so what we need to do is just to plug in this value here in this equation. Okay, how can we do that? Here I have psi and here I have psi xyz time, and I have broken it up into psi xyz and phi t. So I just have to put this value here. Okay, I just have to put this value here. So next thing that I'm going to do is just write the Hamiltonian operator. Here I have written the Hamiltonian operator, and the next thing that I'm going to do is in place of this psi I have to write this. Okay, so what I'm doing is writing this psi xyz, okay, and phi into time. Okay, and on the right hand side of the equation, what I'm going to do is just do this again, minus h cut over iota curly, and in place of psi what I'm going to write is psi x y z and phi into time. Okay, and divide this by curly t. Okay, so what you need to do next is to suppose a system. Okay, suppose a system in which potential energy is independent of time. Okay, what we need to do is just to suppose a system in which our potential energy is independent of time t. So when potential energy is independent of time t, we can say that Hamiltonian operator is also independent of time t. As you can see that the value of the Hamiltonian operator H is equal to kinetic energy plus potential energy. Okay, since kinetic energy has no time variable, only potential energy here depends upon time, and in this system we have taken to be the potential energy or independent of time. Okay, I am repeating this, that my Hamiltonian operator depends upon the kinetic energy and the potential energy, and kinetic energy operator does not contain any time variables, whereas potential energy is dependent upon time. But here we have supposed a system in which potential energy is also independent of time. Since kinetic energy is independent of time, and in our system we have taken potential energy to be also independent of time, so I can say that my Hamiltonian operator in this case will be independent of time. I can say that my Hamiltonian operator will be independent of time in the case in which my potential energy is independent of time. Okay, so if my Hamiltonian operator is independent of time, so my equation will take a form, this phi t will go out. Okay, this phi t will go out, and my Hamiltonian operator will be applied on psi. Okay, will be applied on psi x y z. And the next thing is, so on the right hand side of the equation you can see that I have minus h cut over iota, minus h cut over iota, and I have curly derivative being applied on this part. As you can see that my derivative is with respect to time. Okay, my derivative is with respect to time, and this psi here depends only on the position and it does not depend on time. So this curly cannot be applied on this psi. This curly will directly apply on phi, because phi depends on time and this curly is with respect to curly t. Okay, so following this psi xyz will go out because it does not depend upon time, and this curly will be applied directly on phi because phi is dependent on time and my curly is with respect to time. Okay, here is curly t. So the next thing that we are going to do is to divide both sides of the equation by psi xyz. Divide both sides by psi x y z and phi t. Okay, so I'm going to divide psi xyz and phi t on both sides of the equation. So what I'm going to write is, as you can see here, I have phi t h operator being applied on psi x, y, z, and on the right hand side of the equation I have minus h cut over iota psi x, y, z curly phi t over curly t. So next thing that I'm going to do is just to write psi xyz and phi t in the denominator. I have psi x, y, z and phi t, and here I also have psi x, y, z and phi t. As I have told you earlier here that this equation is a partial differential equation that contains the time variable as well as the position variable. So what we need to do is just to separate this equation into two equations, in which one equation contains the position variable and the other equation contains only the time variables. So how can we do this? As I have told you earlier that what I am going to do is cancel out the time function on the left hand side of the equation and cancel out the position coordinates or position function on the right hand side of the equation. So this is how I'm going to do this. I'm going to cut out the time function from the left hand side of the equation, and I'm going to cut out the position function, position psi, from the right hand side of the equation. Okay, so my final equation will take a form just like this. Okay, so we will have a Hamiltonian operator being applied on psi x, y, z, and I have psi x, y, z in the denominator. Okay, and that is equal to minus h cut over iota 1 over phi t curly phi t divided by curly t. Okay, so now I'm going to compare this with my previous equation. As you can see here that my phi t has cancelled out with phi t. I have h operator being applied on psi xyz and psi xyz. Okay, similarly I have h operator being applied on psi xyz, psi xyz. Is that I have curly phi t divided by curly t, and here curly phi t divided by curly t. So proceeding on, the next thing that you need to do is we are taking both of this equation to be equal to e. Okay, so the next thing what we are going to do is just to take both of this equation to be equal to a constant e. Okay, so on breaking it up, I can say that my h psi x y z divided by psi x y z is equal to a constant e. Okay, and here my this part is also equal to a constant e. 1 over phi t multiply curly phi t divided by curly t is equal to e. Okay, so now take this part of the equation. Okay, on taking this part of the equation, as you can see, what I can do is multiplying this with here. Okay, so this part of the equation will go here, h psi x y z, and this part will go here, e into psi x y z. Okay, so here as you can see that this part is the time independent Schrodinger wave equation, also called the amplitude equation. Okay, so if I drop this xyz, as you can see that it is h psi equal to e psi, and this is the famous form of time independent Schrodinger wave equation. This is time independent Schrodinger wave equation. Okay, so it is also known as the amplitude equation. Okay, so the next thing that we have is the right hand side of the equation. Okay, since we have taken the left hand side of the equation to be equal to e, and I have just derived the time independent Schrodinger wave equation. Now if I take the right hand side of the equation to be equal to e, just like I have taken it here, so taking this equation again, what I am going to do is, so now I am going to take minus h cut over iota 1 over phi t curly phi t divided by curly t to be equal to e. Okay, what I have done is just took this right hand side of the equation to be equal to e. So the next thing that I am going to do is just to multiply this iota here, and minus h cut will go down here, and this phi t and this curly t will go here, and this phi t will come just beneath it. So first of all, what I'm going to do is take iota here. Okay, so I have iota, and this h cut will go down, and h cut has come down here, and this minus has also come here, and the next thing that I have on the right hand side of the equation is e, and this curly t will also go here, and I can write this curly t, since curly is a derivative, so I can also write it as dt. Okay, so my dt has gone here, this curly t has gone here, this h over iota has gone here. What I'm left with is curly phi t divided by phi t. Okay, so that is what I'm left on the left hand side of the equation. Okay, so the next thing that I'm going to do is taking the integration. So on taking integration on the left hand side and the right hand side, I can write it as curly phi t divided by phi t is equal to, since as you see that minus iota is a constant and h cut is also a constant and e is also a constant, so they will go out of the integration. So what I am left with is dt, and my integration will be applied on dt. So applying the integration, you know the rules of integration. On applying the integration here, I get an answer equal to natural log phi phi of time is equal to minus iota over h cut e, and this applying the integration on dt, I get an answer t plus ln of n. So here n is a constant. So now we will take exponential on both sides. Okay, taking exponential on both sides. So on applying the exponential on both sides, here my exponential is being applied on natural log of phi into time, and here my exponential is being applied on this part minus iota over h cut e into t. Okay, and my exponential is also being applied on natural log of n. Since my exponential and natural log will cut down, this exponential will cut down with this, what I am left with is phi of time. And similarly on the right hand side, when this exponential will be applied here, I get an answer equal to e minus iota e t over h cut, and here my exponential will also cut down with natural log. Okay, and this plus will change into multiply, as you know the rules. Okay, and this n will come here. Okay, this plus will change into multiply. Okay, and this n will come here. Okay, so the next thing is the time. This is what you are seeing right now in front of you is the time dependent form of the Schrodinger wave equation. Okay, this here is the time dependent form of the Schrodinger wave equation. Time dependent form of Schrodinger wave equation. Okay, so now I have psi. Going on the start, what I did was breaking up this psi x, y, z, t into psi of the position coordinates and phi t. So what I did was this in the start. As you can see that here I broke up this psi xyz t into psi xyz and phi t. So I have just written this here. Okay, so I have the value of phi t. What I'm going to do is place the value of phi t here. Okay, so putting the value of phi t here, what I get is psi x y z, and in place of phi t I'm going to write n e raised to power minus iota e t divided by h cut. Okay, so this whole is in the power of e. So the next thing that I'm going to do is to find the total probability density. Okay, so I'm going to find the total probability density. Moving on to the next page. So the next thing I'm going to do is finding the total probability density. So as you know that total probability density is given by psi square. Okay, total probability density is given by psi square is equal to, from negative infinity to positive infinity, I have psi hysteric. Okay, I have d tau. So next thing that I'm going to do is just to plug in this value. I'm going to plug in the value of psi x by t, this value here, okay, and here. So plugging in this value, I get, in place of psi, I am going to write minus infinity to positive infinity. I am going to write psi x y z, okay, and the next thing is here ne minus iota et over h cut. So I am going to write this here, n e minus iota et over h cut, okay. This is the value of my first psi, and now I'm going to write the value of psi hysteric. Psi hysteric also has the same value, but there will be one small difference. The small difference will be the value of sign. Since this was the simple psi, so here I have taken it just to be the same, okay. And here is psi hysteric. Psi hysteric means complex conjugate. In complex conjugate, as you know that we change the sign of iota, so here I am going to change the sign of iota towards positive, so my equation will become just like this, okay. So next thing I have is d tau. Here is my d tau, okay. So as you can see that here minus iota and positive iota will cut down. This will cut down with this. I have n and n. This n will multiply with n and I get an n square, and this n square will go out of the integration. As you know that n is a constant, minus infinity to positive infinity. This n square has gone out of the integration, and the next thing I am left with is psi and psi hysteric, okay. The next thing I am left with is psi and psi hysteric d tau, okay. So now I haven't put the bar above and below this psi because this psi is dependent only on the position coordinate. Similarly, this psi is also dependent only on the position coordinate. The time coordinate has cancelled out. So I can say that my total probability density psi square is independent of time, okay. I can say that my total probability density is independent of time. So the next thing what I'm going to do is the average value or expectation value, okay. The average value or expectation value of any observable property of a system. The next thing what we are going to do is just to take the average value of any observable property of a system that is given by A. Here is my average value, okay, and this one is equal to A bar, and here I have used the mean free theorem. Just like I've used in my previous video. I have psi hysteric and my operator being applied on psi d tau. Since I'm going to take the average value, so I have to divide the same, minus infinity to positive infinity psi hysteric So what I have here is psi hysteric and operator being applied on psi, and here I have psi hysteric and psi d tau, okay. So I have this here. So next thing what I'm going to do is just to plug in the value of psi hysteric. As you know, the value of psi hysteric was psi hysteric depending upon xyz, and I had the time variable here. So I have just written the time function here, and the next thing is operator A being applied on the other side. Here the other side is psi xyz and my operator of time, and my time part of the equation, okay. And here is the time part of the equation. As you can see that here the psi was psi hysteric, so I have taken the iota to be positive, and here the psi was simple psi, so I have taken iota to be negative, just as the value that I have taken before, okay. So then in the denominator I have psi hysteric, so here is my psi hysteric depending on the position coordinate, and I have this time factor here, and the next thing is psi, the simple psi here, and this simple psi is psi xyz, and here I have written the time part of this equation that contains minus iota. As this was a simple psi, so I have taken the minus iota here. Okay, so the next thing what I am going to do is, as you can see that this will cut down with this part will cut down with this part, and this part will cut down with this part. Okay, so what I have been remain with is n multiplied by n square and n multiplied by n square. Since n square is a constant, it will go out of the integration, and n square on coming out of the integration, I am left with minus infinity to positive infinity psi hysteric x y z, and operator A being applied on psi x y z, and in the denominator I have psi minus infinity to positive infinity psi hysteric x y z, and this n forms n square, which will go out of the integration. Okay, and I am left with psi x y z. Okay, I had d tau here, I also had d tau here, and I am going to write d tau and d tau. Okay, so the next thing that you can see is this n square will cut down with this n square. This n square cuts down with this n square, and if my psi is normalized, okay, if psi is normalized, if my psi is normalized, I can say that this part is equal to 1. Okay, if psi is normalized means that this part here, the probability of finding the particle will be equal to 1. So this part here will be equal to 1. So I can take this part to be equal to 1, and I am gonna left with only the upper part of the equation, because this part will become equal to 1 because psi is normalized. Okay, you remember the rules for the normalization. So what I'm left with is a average value with minus infinity to positive infinity psi hysteric x y z, and operator A being applied on psi x y z d tau. Okay, so I can just drop these subscript, because as you know that this psi is dependent only on the position coordinate. So therefore the observable property what I have calculated, the observable property is independent of time. Okay, since as you can see here that the average value or expectation value of any observable property, what we were finding the average value or the expectation value of any observable property, and after applying this, after finding this, we have come out with this solution, and this solution does not contain any time coordinate. So I can say that my observable property is independent of time. Okay, I'm going to repeat it again, that what we were going to do was we were finding the average value or the expectation value, we were finding the average value for an observable property, and after finding the average value, we have come out to be with the solution, with this solution we have come out with this solution, and this solution does not contain any time variable. So I can say that my observable property does not depend upon time, it is independent of time. So this system, okay, since my observable is independent of time, okay, my observable is independent of time, so I can say that this system is said to be stationary state. System is said to be stationary state system. Okay, this system is said to be stationary state system. Okay, all its property, what does it mean? That all of its properties can be obtained by solving time independent Schrodinger wave equation. Okay, so as you can see that the probability density has come out to be independent of time, and my observable property has come out to be independent of time. So I can say that this system here is a stationary state system. Stationary state system does not mean that a system is at rest, it only means that we can find all of its properties by solving the time independent Schrodinger wave equation. The time independent Schrodinger wave equation is h psi is equal to E psi. Okay, so this side here depends only on the position coordinate. It means that our observable property is independent of time. So this system is said to be a stationary state system, and since it is a stationary state system, so we can calculate all of its property by using the time independent Schrodinger wave equation. So that was all for today's video. Do not forget to like the video and subscribe the channel. Inshallah, see you in the next video.